And there are ways where if they had a close encounter with Neptune, one of them could get ejected and the other one could be captured into Neptune's orbit. And we think then, because Triton, that moon of Neptune, is very similar to the planet Pluto in a lot of ways. And so we think that in that case, it's a capture. Mars has two little moons, they're probably captured asteroids. But most of the time impacts explain.
On Mastering Astronomy, one of the questions it asked about like the rotation of the planets or whatever. And if the answer was all planets move counterclockwise or whatever.
That would be the revolution of the planets,
Yeah.
so orbiting the sun, yeah.
Okay, so like if we were given a question like that, will you say like except for Venus or something like that?
So careful, Venus goes around the sun in the same direction as Earth does. What it does differently is the way it's spinning on its axis. In other words, if you're the sun and I'm Earth, Earth does this. If you look from above, I'm going around you counterclockwise and I'm spinning around my own axis counterclockwise. Venus does this. It's spinning the opposite direction that it's going around. Very, very slowly though. Its day is longer than its year.
How is it possible that there could have been a big collision and like something so perfect happened like that, but it didn't follow its axis?
Well, it would have to have had the right conditions. In other words, yeah, typically you would expect it to have also tilted it. But if it was already pretty much upright and the collision happened in the equatorial plane, like along the equator, then it wouldn't necessarily tip it over. So what it comes down to is the conditions would have to be right for it to happen, but it's certainly not impossible. In other words, the exceptions to the rule, any one of them would be unlikely to happen on its own, but you would expect some unlikely things to happen. Hello.
Hi.
Welcome to the show. Make yourself at home.
So what's the difference between the nebula theory and the heavy bombardment?
The heavy bombardment is the period at the end of planet formation when there was still a significant population of leftover planetesimals that had not yet accreted onto planets. The heavy bombardment was the end stage of accretion, the last stage of planet building. It's when most of the remaining planetesimals that were going to become part of the planets did so. When you look at the craters on Mercury, for example, you are looking at scars of the heavy bombardment. Those were formed by planetesimals that smacked into Mercury and became part of Mercury, is what it comes down to, but they left scars when they impacted the surface.
In my notes, I have the cause of the craters on the moon is from heavy bombardment.
Yep,
Okay.
the heavy bombardment caused most of the craters in the solar system were formed during the heavy bombardment.
Gotcha, just double checking.
Yep, yeah, I just picked Mercury because I wanted to pick something, but yeah. Most craters in the solar system are a relic of the heavy bombardment. Not all of them, but most of them are.
You might have addressed this, but why is the tidal bulge increasing likely in the distance between Earth and the moon?
Yeah, so in that case, it's because the Earth is spinning certainly faster than it is going. The Earth is spinning faster than the Moon is going around us, right? And so, in other words, how long does it take the Earth to spin once on its axis?
A day.
Right. A day. How long does it take?
50 minutes.
Yeah, right. It takes. That's all I'm looking for is it takes you, right? 24 hours. How long does it take the Moon to go once around us? Yeah, okay, in the spirit of a day.
The rotation of phases,
I'm looking for something simpler than that.
1 month.
A month, yes, a moon. A moon, right, yes, right. So Earth is spinning a lot faster than the Moon's going around us, okay? So before, we said, oh look, the tidal bulges point towards the Moon. Okay, well, I exaggerated because the Earth is spinning. And as a result, it's dragging its tidal bulge a little bit, it's dragging the tidal bulge a little bit ahead of the direction to the Moon here. In other words, the tidal bulge doesn't quite point to the Moon. The friction with the spinning Earth makes the tidal bulge point a little bit ahead of the moon over here. Okay? So what does that mean? Well, that means that the moon's gravity is pulling on this tidal bulge, and it's pulling on this tidal bulge, but notice, if it's pulling on this tidal bulge, and this tidal bulge is a little bit angled, then the moon is trying to realign the tidal bulge, so to speak. In other words, it's pulling partly downwards on this tidal bulge here. If you imagine the moon's gravity as being like a string pulling on this tidal bulge right here, if I had a string attached to this and I pulled on it, what would tend to happen? It would tend to line the tidal bulge back up again. It would want to pull this down. See what I mean? Like if I had a string here and I pulled on it, it would try to make the tidal bulge come back down again. So the moon is pulling back on this tidal bulge right here. And as a result, notice that that's going to produce a torque that tends to slow down the rotation of the Earth, is the idea. The moon is pulling on this tidal bulge this way, while the Earth is spinning this way. So it's tending to slow down the rotation of the Earth a little bit because of the way it's pulling on that tidal bulge that is dragged ahead of it a little bit. And so Earth's rotation is literally slowing down because of this effect, because of the moon's gravity pulling on its tidal bulge. And if Earth's rotation is slowing down, what's happening to its rotational angular momentum?
Decreasing.
It's decreasing. But the total angular momentum has to stay the same, so the Earth's decreasing spinning angular momentum is being compensated by an increase in the moon's orbital angular momentum, or in other words, the moon is moving away from us.
Because I'm farther away on the orbital motion.
The way it's picking up angular momentum in moving away from us. Or put another way from it, the tidal bulge is pulling on the moon forward a little bit. The tidal bulge is putting a force on the moon, which is partly in the forward direction, which is speeding the moon up. Or attempting, if you will, to speed the moon up. But actually, it's complicated. It slows it down in the end because it's getting further from us. But what it's doing is it's, in a sense, flinging the moon outwards from us. So the moon is getting further away from us, and at the same time, the Earth is slowing down its rotation. And it's all because the tidal bulge is carried forward a bit by the Earth's rotation. The moon's gravity tries to pull the bulges back into line, slowing to Earth's rotation. The gravity of the bulges pulls the moon ahead, increasing its orbital distance, is the idea. If you waited long enough, then you would eventually reach a point where the moon was going around us and we were spinning at the same rate. And so then we would also always have the same face towards the moon. But that would take billions of years to happen.
And then there'd be no time.
Well, no, it's just that Earth would spin very, very slowly, so days would be much longer.
Okay, that's why.
It's not like, and even if the Earth stopped rotating, it's not that time would stop, it's just that Earth would stop rotating. In other words, Earth's rotation isn't causing time on Earth. You could use its rotation to measure time, but it's not causing time to pass on Earth. Despite what the first Superman movie did. The first Superman movie, Superman flies around Earth backwards to make it spin backwards, and that makes time run backwards, so that then a terrible thing that happened to Lois Lane doesn't happen anymore because time goes backwards, and that's the stupidest thing. But anyway, that's not what would
I was
happen.
already confused now.
What's that?
So I was already confused now.
Well, just ignore what I just said. It was stupid. It's not right. It's just not right.
It's not going to be in the exam, so.
No, it's not. It's not. Yeah, tell me. Question 37. What's the stupidest thing ever in a movie? A, Clark Kent flies around Earth.
So we talked about heavy bombardment craters. And can you explain large impact theory, if there's any similarity between heavy bombardment?
Yeah, the large impact theory that formed the moon, we think, wouldn't have left a crater on the Earth because it was so massive that it would have not perhaps completely smashed the Earth apart, we think, but on the other hand, it would have largely shattered it and melted a lot of it and vaporized a lot of it, So in other words, the Earth had to largely reform too, and so there's no scar left by the impact. But then the moon would have accreted out of material, where's it going? The moon would have accreted out of material, oh, that's the wrong chapter, that's one. The moon would have accreted out of material that was tossed out of the Earth by that titanic impact. So, yes?
So like, when the dinosaurs like got extinct or whatever,
65 billion years ago.
yeah,
Yes.
so did like something like that happen but the Earth reformed or?
No, it was not, so that was a big impact, but it wasn't a giant impact.
Okay.
We think that the Earth was hit by either a comet or an asteroid that was roughly 5 or 6 miles across. So 5 or, you know, that's only like that's less than 1/1000th of the Earth's diameter. So in other words, if the Earth was like a meter across, this thing would be less than a millimeter in size. But on the other hand, something that large produces a tremendous amount of, deposits a tremendous amount of kinetic energy when it hits the ground, and so it would throw up huge amounts of dust into the atmosphere, and it would tremendously heat the atmosphere such that there would be catastrophic worldwide effects that would cause a mass extinction. It will happen again. It's only a matter of time, unless we have our guard up. In other words, if we monitor for these things and you detect one far enough into the future, then you could deflect it before it hit the Earth. Not in the way Bruce Willis does in that silly movie that came out like some number of years ago. But there would be ways to, if you saw it far enough away, you could deflect it and save civilization.
Okay. Another question. Okay, can you go over what like differentiation is with the core mantle?
No, because I accidentally put that on this and it's really on the final, because that's in chapter 9.
So I can delete that
Yeah,
from the
you can
study
delete that,
guide?
as a matter of fact.
Lessons.
Yeah.
Even though I'm
No, it's just what, like the denser things come,
The denser things sink to the
Sink to the
center and the
middle.
lighter stuff flows to the top. So it's not difficult, it's what happens when
Those
you
are
shake
mini
the top.
quiz, right?
What's that?
Those are
Yeah. But you know, no, that was chapter 9. Whoops, you know. It's just all in my head, so sometimes I forget what's in what chapter, you know. So I forgot that wasn't in this chapter.
I'll ask.
Yeah, go for it. Yeah.
Can you, like, what's the difference between like a planetesimal and a protoplanet?
Size.
Okay.
And
That's
there's-
what's turned into protoplanet.
Yeah, right.
Yeah.
Just like a certain, like when does it actually change the one? It's just like they've accumulated so much.
Yeah, but you know, it's one of those things like, you know, like Jupiter, you're basically like, you know, how big does something have to be going around a planet before it's a moon as opposed to just a big boulder? There's no definition. In other words, there's no hard and fast definition. You can arbitrarily say it has to be bigger than so many, whatever, but nobody's done that. It's fuzzy, but it doesn't matter,
Okay.
is what it comes down to.
They're both just.
They're both planet building blocks, yeah. Roughly speaking, a protoplanet is big enough that if everything stopped and it was orbiting without other large protoplanets nearby, you'd call it a planet. Protoplanets are big enough to be planets. Okay, well, how big is that? You know, it's roughly speaking big enough to crush itself into a sphere.
They're bigger
You
than
call it a
Pluto?
protoplanet. Well, Pluto's big enough to be a planet, but the reason we don't call it a planet is because it hasn't cleared its orbit. In other words, it's not the only body of that size in its region of the solar system.
Okay.
And we've made that part of the definition of a planet. The moon is big enough to be a planet. Why don't we call it a planet? Because it's going around us. If the moon were orbiting the sun separately, it would be a small planet. We call it the smallest planet in the solar system, the moon, if it were orbiting. And we wouldn't call it the moon, because it wouldn't be a moon. Luna, smallest planet in the solar system, if it were orbiting in its own separate orbit. there's always that point, it's like, who's going to say like, nope, that's it, I found it.
I guess.
I'm trying to reach that. Anyway, yes.
What can we expect kind of about, we talked about isotopes earlier, like what should we be, you don't know if you can answer this, comfortable identifying pictures or just a multiple choice about what is an isotope and what makes that different?
Yeah, either one. But I mean, if you had a picture and, oh, look, here's something with 6 protons and 6 neutrons, and here's something with 6 protons and 7 neutrons, to recognize those are isotopes, or something like that.
Okay.
But know what an isotope is,
Okay.
Same number of protons, different number of neutrons, they're isotopes of the same element.
How far in depth are we gonna have to know, like the chapter 7, like slides about the difference between terrestrial and Jovian planets and like?
So you should know the properties in terms of, if you have, so in particular, you should recognize like, terrestrial planets are rocky, metallic,
Right.
canyons, craters, blah, blah, blah. You should know things like that.
You're not gonna ask like which planet is 4 times larger and
No, I'm not having you,
times its mass.
well, careful. So, as I had mentioned, there is one particular slide where I do want you to know the numbers. So I actually do want you to know the numbers on this. So, by that I mean that I want you to know how big Earth is,
Yeah.
right? Either in miles or kilometers. I want you to know that it's 6 trillion kilograms, 6 × 10⁻24 kilograms. And then I do want you to know Venus is about the same size, Earth is half the size, Mercury is about 2/5 the size,
Okay.
that the mass is about 1/10 and 1/20. I actually do want you to know those things. I have a table where I want you to fill in those numbers.
Jesus.
Yeah. And that's why on the study guide I said this is something, look at it every day and you'll memorize it by accident. Was that? No, you do. Now again, so I want you to know about 1 gram per cubic centimeter. I don't want you to know 0.7 versus 1.7,
What
which you should know.
about, this is just a range, so we just have to name the range?
You should know that it's about 1 gram per cubic centimeter for the Jovians and about 5 for the terrestrials. You don't have to know that it's 4 for Mars and 5.5. Just 5 is good enough. 5 times the density of water. And I do want you to know 0.4, 0.7, 1, 1.5. This one's actually easy if you think about it. If you know how far Jupiter is 5, double it, you got Saturn, double it, you got Uranus, and don't double it, you got, right? Notice 5, 10, 20, oh, third. Right? I mean, 5, 10, 20, well, go another 10. Or look at it as like 5, double it, you got 10, now keep going by 10s. So I actually do want you to know those numbers. There is a table there. Because if you have, again, I don't want this to be all about memorizing a zillion facts, but there's kind of basic facts. If you have no idea how big Jupiter's orbit is compared to Earth's orbit, that's an important thing to be missing to try to understand the solar system. If you have no idea that Jupiter's how many times more massive than Earth, then you're missing a piece of information. So, again, I only want to do this kind of precision, so I would argue it's not terrible. 300, 100, 15, 15 for the masses. For the diameters, 10, 10, 4, 4 for the Jovian planets. So there's a lot of similarities there. For these purposes, I'm saying Jupiter and Saturn have the same diameter, 10 times that of Earth. Uranus and Neptune have the same diameter, 4 times that of Earth. For their masses, Jupiter's 300, Saturn's 100, the other two are 15 and 15. It's not exact, but it's close enough. So,
Cool beans.
cool beans, I know. Yes. Honestly, too, this is the kind of thing where, if you're going to be staring at one thing before the test starts, that's the thing to be staring at, right there. That will have the maximum payoff is burning those numbers into your brain right before the test, or re-burning them in. If there's anything you're doing right before the test, it's looking at this.
Turn to that the first thing you do.
Yeah, and then turn to the page that has that table in it and do your brain dump. Yeah.
So this is effectively the only quantitative stuff we need to know.
Yeah, in terms of like detailed numbers or whatever, yeah. Uh-huh. Yeah. Mhm.
Could you just elaborate, or at least give, I didn't have really specific notes on how, I think it was the Tyco supported, it was like the first bullet we had.
Tycho and Kepler.
Yeah, so Tico, I've looked it up and it is more, I know Amanda said Tyco, but I've looked at, the weight of the evidence is for Tico. But you're kind of not, there's different ways to say it, But anyway, Tycho's observations, Tycho was the greatest naked eye astronomer, and Kepler used his observations to come up with his laws of planetary motion. That's what I want you to know.
Perfect, that's what I heard. Fantastic.
Which one was the one that had like Earth and then like Earth was the center?
Tycho had everything's going around Earth. Everything's going around the sun except for Earth. In other words, he had a model where everything goes around the sun, and then the sun goes. Everything else goes around the sun, and the sun goes around the Earth.
And then Galileo was the one that was like.
Well, Copernicus came first and said, he wasn't the first person to say this, but Copernicus had his model of everything goes around the sun.
Right.
Tycho's like, I think everything goes around the sun, except everything else goes around the sun, but the sun goes around the Earth. Galileo's observations of the moons of Jupiter and of the phases of Venus were consistent with Tycho's model. They don't make any sense in our modern understanding of gravity.
Okay.
It wouldn't make sense for the much more massive sun to be orbiting the much smaller Earth. But if you don't know how gravity works, just in terms of the motions, Tycho's model was consistent with Galileo's observations.
Cool.
Is that thing still blinking red?
Yeah, it's kind of blinking a little bit faster.
Is it? So I don't know if it's like saying like, I'm getting hungry. Maybe look if it's got an indication of where its battery is. It claims that it's got 67 minutes left. So okay, let's see if we can run the battery now. Another 67, right? No. I mean, if you want to, I could be here all night. But, I mean, at the end, I'll just be so. Or something, but
What other kinds of things would you be asking open-ended questions on versus multiple choice?
Not the mass ratio. The
Kepler books.
lecture tutorials, the packets, the Kepler stuff, the Kepler's law tutorial. Kepler's second and third law tutorial stuff.
Quick question, epicycles and deference. I have epicycles being a small circular orbit,
Yep.
deference being the large